Don't forget that you have a homework assignment that is due tomorrow on active. And we have a quiz on Wednesday that is covering gas laws, but I'll talk about it at the end of the quiz review. And the calorimetry today. So I will talk about that. Those of you that were not here on Friday, I handed out this thing on extra credit. I had passed out two possible things you can do. They're in the orange and the yellow folder. The orange one is gas laws one. The yellow one is calorimetry. I had way too many individual papers flying around. So this time it has to be either in a folder or attached to a notebook. So they're designed to be small enough that you can fit them in a notebook this size even, or if you want to do a spiral notebook or whatever you can. These are extras. I buy them at Staples for like 25 cents a piece in the summer, and then I have extras to give away. So feel free to take one if you want to. So like the calorimetry one would look like this with the flaps that you can lift up and see the answer so you can test yourself. And then the one's probably best to go to the side so that you can have both pictures right side up. So make sure you are, if you're going to study that for the quiz, that would be a good thing to do. All right, so the quiz on Wednesday, we are going to be looking at doing molar weights for gases. We are going to be looking at density for gases. I will probably pick just one of those. And I'll do like one class will get density, another class will get molar weight, just to have different versions of it. And then there will probably be a question on gas stoichiometry. So remember with gas stoichiometry, and if you like, you can use your slider. If we start with a solid, and that's probably the easiest thing for me to do, to say, oh, we're going to create a gas by, like you did in lab, take magnesium and divide it in, or not divide it, dissolve it in acid. So we have the mass of that solid. We're going to divide by the molar weight, do our mole to mole ratio, and then from there, switch that over. I'm not looking for concentration. I'm looking for something about my gas. So I want volume of gas, not volume of solution. So just make sure you're on the right thing. If I ask for the pressure of the gas, just swap the pressure and the volume in this calculation. I just didn't want to make the slider too big. Yeah.
What did you say was going to be?
So the first one either finds density or molar weight. And the second one is going to be doing stoichiometry with a gas. So probably something like you take this solid and its reaction is going to produce a gas. You're going to start with the mass, and then you're going to tell me what volume or what pressure you get from that gas. And if you get pressure instead of volume, remember you can just swap where pressure is, put pressure here, and then put volume on the bottom there. Those are interchangeable.
And we can use that.
And then you can use that. Okay. I will also be asking you about units for energy, and there will probably be a question about the Q equals MC delta T calorimetry question. So we're going to go over that here in just a minute. Okay. And you should know the first law of thermodynamics. So we talked a little bit about the first law the last time. The first law of thermodynamics is often called conservation of energy. So I didn't tell you guys that. I mentioned it in my other classes. But just like we have conservation of mass that says before and after the masses weigh the same, this one is the same idea with energy, but it's for the entire universe, not just for what we're looking at. Okay, so we're going to use the idea of conservation of mass. And the way that this is connected is that if this iron that we measured was 445 joules that it lost, if it's losing that energy, it has to go somewhere. It doesn't just disappear. And where it is going is its surroundings. And so technically it goes in all its surroundings, but what we can measure is the water. So we're going to assume the water is the surroundings. And so what we're going to do is we're going to say, however much energy went out of here, went in here. So we're going to do a calculation using that same formula. And I'm going to write down the information and then I'm going to turn off the screen. Well, actually, I don't need the screen from there, but we had the Q of the iron was negative 445 joules, and the mass of the water is equal to 155 grams. And the temperature final of the water says it rises, no, what temperature will it be at? So that's what we're looking for. And the initial temperature is 22.5 degrees Celsius. All right, so we do have to get the C for the water. So last time, stay down. Last time we used iron, the 0.45, but this time it's water that's changing its temperature. So we're going to go down here to water, and we'll use this a lot. You'll use it in lab as well. And you'll notice it has the most sig figs. That's the one we understand the best. So 4.184. I will always provide it to you, but it's likely you will remember it. So C for water is 4.184. We're going to say that Q for the iron is the opposite of Q the water. And this is where people get confused. This doesn't mean it's a negative number. It means whatever the sign of this is the other sign, okay? So negative 445 joules for the iron is equal to the negative of whatever this is. So we can multiply both sides by -1. The Q of the water is the positive. Okay, so, or you can think of it as just you change the sign. But a lot of times people look at that and they're like, oh, it's supposed to be a negative number. No, it's not supposed to be a negative number. It's supposed to be the opposite number. And then we're going to use the formula Q equals MC delta T. So this number is equal to 155 grams times the 4.184 that we got from the chart, joules per gram degrees Celsius, or sometimes remember you'll see per Kelvin, but you don't have to switch it to Kelvin because we're subtracting those numbers, and the size of a degree is the exact same size of a Kelvin. It's just they're shifted down the scale. So when we're subtracting the two numbers, the difference will be the same. And then we're looking for T final. So T final minus, I didn't leave myself enough room, 22.5. All right. So we've got 445 joules. I want to get that temperature by itself. So I'm going to divide by this and this. 155 grams and 4.184 joules per gram degrees Celsius, right? But that doesn't get temperature by itself. I'm still left with TF minus 22.5. Okay, so I'm going to solve this first, and then I'm going to take care of that. So to undo this multiplication, we divided. When we get the next number, we're going to undo subtraction by adding. Okay, so try plugging that in, see what you get. I get a number that's less than 1. All right, Andrew, do you have a number yet?
0.686.
That's what I've got. We've got at least 3 sig figs on each of those, so I'm going to go with that, 686, and the next number is 1, so we'll just leave it at the 6. My joules have canceled and my grams have canceled, so this is per. Oh, no, wait, because that's on the bottom. So this ends up being degrees Celsius. All right, and that's equal to TF minus 22.5. Now, this is where the sign matters, because if I have a negative here, when I move this over, I'll get a different number than if this were positive. This is telling me that the change was positive. The water got warmer. So what happened? Remember, we started with this iron, this hot piece of iron, and we dropped it in the water. Should the water get warmer? Yeah, it should get warmer. So we're going to add 22.5 to both sides. And then we kind of have to remember our rules for adding in sig figs. Okay, so this side, we got TF by itself, that's all good. But this side, I'm going to end up with 23.186, but I only have information to that tenths place. So I can't keep the 8.6. Now I can use it to round. So I can say this is 23.2 degrees Celsius. Okay, so we're not paying attention to 3 sig figs and 3 sig figs. It's true they both have 3 sig figs, but when we add and subtract, we're not counting sig figs, we're counting decimal places, and we only have 1 decimal place that is in common. All right, so that's how we do that side of things. And we're going to see a couple more examples of that as we go along. So calor means heat and has to do with, and metry has to do with measurement. So this is measuring heat. And the way we're going to do this is with what's called a coffee cup calorimeter. Now we're literally going to use a coffee cup, but we can also use other types of containers. So the insulated containers, the coffee cup, we're using constant pressure. If we use a bomb calorimeter, we have it all in a sealed container. And so that's going to, if there are any gases that are made, it's going to keep them at the same volume, but it's going to change the pressure, because if we make gases, it'll increase the pressure. If we use up the oxygen and make a solid, then it will go in the opposite direction. We won't deal with bomb calorimeters. So what we assume is that most of the heat is staying with the reaction, but some of it does get absorbed by the calorimeter. We in class will assume this is negligible, which means near zero. Okay, so this is what it's going to kind of look like. Of course, we use the digital thermometers now. We will stack 2 styrofoam cups just to make sure that all that heat is staying inside and not getting out into the air in the room. We sometimes use a stir, sometimes don't. It probably won't have paddle wheels like this one. It'll probably just have a loop so that you can kind of stir it. Be careful not to jam it into the bottom, stay in the water, because if you jam it into the bottom, you get a hole in the bottom of the cup and then your water leaks out and your experiment's ruined. So don't do that. But other than that, this pretty much looks like what we're going to be doing in lab. You'll have a lid that's like a normal lid for you go to a restaurant. It's got that little X in the middle that you stick the straw in, and instead you're going to stick your thermometer in. All right. Let's see, do I have, nope, I don't. All right. There is a picture of a bomb calorimeter on the screen here in the classroom. It's not real important because, like I said, we're not going to be using that. But it has an inside container where the reaction is, a whole bunch of water around it that absorbs any energy, and then the thermometer measures the temperature of the water change. So that would be how they would measure like the content of calories of food. They would burn a small sample of that and see what it is. And then once they get a good idea of like how much is a potato or how much is an egg, then they just base it on what are the ingredients of this rather than going through and doing the experiment. Okay, so in a calorimeter, the system can be hard to measure. Like I said, we can't stick the thermometer in the piece of iron. So what we do is we measure the surroundings. The calorimeter is designed to contain the heat so that the surroundings become just the water, and you don't have to worry about measuring the air and your hand and all of those things. So the water is going to absorb the vast majority of the heat. In reality, if you've ever had a styrofoam cup with a hot drink in it, you know that it feels warm. So some of that heat does escape. So in lab, you're going to account for this absorption. That's going to be the heat capacity of the calorimeter. In class, we're just going to assume it's 0. So here where it says, we often assume the cup, the thermometer, et cetera, don't absorb the heat. That's what we'll do in class. It'll be this perfect ideal world. In lab, you're going to test hot water and cold water. And since they're both water, they should meet exactly in the middle, and they're not going to meet exactly in the middle. And so you're going to say, okay, whatever difference there is between that, that's how much was absorbed by the cup instead of by the cold water. And therefore, that's the heat that it absorbs. And then, so we go back to this idea from conservation of energy that Q, or heat of the surroundings, which is the water, is the opposite in sign, but the same value as the Q of the system. And that's why we said the 445 joules that was negative for the iron was equal to the positive 440 joules for the water. And that's pretty much how you're going to do this in lab. I think you have 2 weeks of this. And so you're going to do one where basically you're just looking at water and a piece of metal. And then you will do one where you have a solution. So when you have the solution, you're going to have an acid and a base, and you're going to mix them together. And when you mix them together, the acid molecules and the base molecules are going to get together and do the reaction, but there's also going to be water there. So even though they're all mixed together, the system is the molecules doing the reaction, the acid and the base. The surroundings is the water. Okay, you're measuring the temperature change in the water. Most of what's happening is a lot fewer molecules of the acid and the base. Okay, so here's another example, because I said on your quiz you're going to have something like this. Let's say we have 180 grams of hot coffee, and is it at 75 degrees Celsius? Now, 60 degrees Celsius would cause a burn, so 75 degrees would cause a severe burn. So we want to cool it down. Our system is the coffee, and it has a mass of 180 grams. And we got the little decimal there giving us 3 sig Vicks. So we're going to cool it down, and we have water that is at 18 degrees. So temperature of a cool room. And we want to know how much water are we going to need to cool this down to 58, because we know 60 is going to be too much. That's going to burn us. But 58, that might be something that we can take sips of it and blow on it and get it down to a good temperature. Okay, so we have 3 temperatures. So we have initial and final temperatures for both the coffee and the water. This is something you need to know for lab. The final temperature for both is the same, because we want the coffee to cool down to a temperature, and we want that cool water to warm up to the coffee temperature, right? So they're going to meet, not exactly in the middle, but somewhere in between. So the final temperature is the same for both of them. And that's going to be true in lab and whatever calorimetry you do. Final temperature is the same. The initial temperature, you have to pay attention to which is applying to it. So in the case of the coffee, the initial temperature is the 75. In the case of the water, it's the 18. Now, because coffee is mostly water, we're going to make the assumption that it also has a heat capacity of 4.184, and that should be pretty accurate. All right, so let's keep track of all of our variables that we have in here, because we've got the Q equal MC delta T, and we got it for both sides. So we have the mass of the coffee, the heat capacity C is the same for both of them. We have the initial temperature of the coffee and the final temperature of the coffee. We have the initial temperature of the water, and we have the final temperature of the water, but we do not have the mass of the water. That's what we are looking for. All right, so we are going to use that Q equals MC delta T equation twice. Since for the coffee, we have everything but Q, we're going to start with that, and we're going to figure out what Q is. And then we know that the magnitude, or how big it is the same for the coffee and the water, but we're going to switch the sign. So if it's negative, it will become positive. If it's positive, it'll become negative. I still see pens moving, so I'll wait just a second for you to catch up. All right, so as I said, Q is system, opposite of Q of the surroundings. Our system is the coffee, water is the surroundings. So Q of the coffee is MC delta T. So we're going to plug in those things that we know. 180 times 4.184, and then 58 minus 75. So remember, it matters which order you put them in. So our final temperature is lower. So we're going to get a negative number. The heat is leaving the coffee. All right, so I'd like you to plug this into your calculator and see what you get. I do have extra calculators up here if you need them. But especially since we have both the multiplying and the subtraction within the parentheses, that's something that is easy to mess up. So make sure that you give it a try and see what you get. All right, so I got something that was negative 12,803. So remember, we're going to get big numbers for energy. That's not too surprising. If you did not get this, what I would suggest is do the subtraction first and then put that into the multiplication, because probably having both of those in there at the same time, trying to do it all at once, is what's causing the problem. Okay, how many sig figs do I get? 2. My temperature is going to come down to a temperature that only has 2 digits to it. This is why we want to make sure that we write the decimal point on the thermometer in lab, so we've got that extra decimal place. So I'm going to have to round this again to negative 1,300 joules or 13,000 joules, and that would also be negative 13 kilojoules. So we'll talk more about kilojoules when we get to chemical reactions. All right. That was our coffee. Our coffee is the same as the water, but opposite in sign. So water is going to be a positive 13,000 joules. Okay. So now we have Q, we have C, and we have delta T. So the only thing we're looking for is the mass. So if you want, you can rearrange the equation so that you have mass by itself. Mass is equal to Q over C delta T. And then all you have to do is plug it in. Now, ideally, we're not going to add nearly as much water as we would have for the coffee, unless you just don't like coffee. But, you know, you don't want to dilute your whole drink so you can't taste it anymore. So hopefully this mass is somewhat less than 180. And I get 78 grams. So know how to use Q equal MC delta T for your quiz on Wednesday. That's the big picture here. Questions? All right, I will see you on Wednesday. And don't forget that if you have a problem with moving the test to Wednesday, please email me and let me know, because if it's on the syllabus, I don't want to change it unless it's okay with everyone.